So I'd probably divide this up like this. It doesn't matter. There's a lot of ways you can divide it up. I'm going to do it that way. So this first piece here is 8 by 36, which is going to give us what? 288, I believe. Centimeters squared. Somebody double check that for me. Okay. This piece here is 16 by, what's this? 22? So what's that, 352? And this piece here is 28 by 12? $236 or 336, sorry. So 986 centimeters squared for the area of that base. What you guys came up with? 976? No, I'm getting 986. No, 76. You are correct. 976. Does that look better? Okay. So the volume is 976 centimeters squared times the 20 centimeters of height. $19,520 centimeters cubed. Does that look right? Perfect. That's the volume. How many milliliters is it? If it's water, how many grams is it? So that means for kilograms, it's 19.52.
I thought because it was centimeters cubed. Or no, never mind. Never mind. I thought it's
You leave that up there.
Yep, I'll leave it up there for a second. I'm sure there is, but I've given it to you a couple of times too to copy down. The one I put is probably better than the one in the chart. I think the one in the book goes up and down instead of side to side.
I might have it.
Check the back of your notebook. Okay, so today we're going to start out with a challenge. Yeah, I know, a different challenge. I'm going to challenge you to answer this question. If I told you I can throw a baseball at a rate of 90 feet per second, would you believe me? That's saying if I'm standing on first base and I throw the ball to home plate, I can get it there. Once I release it, I can get it there in 1 second. Well, what are we used to seeing speed in? Miles per hour. So let's convert this into miles per hour. Now, normally when we did unit conversions, measurement conversions, our first step was to make it a fraction by putting it over 1. Well, this is already kind of a fraction because it's got that fraction in the rate here, feet per second. That is 90 feet per 1 second. So it's already a fraction. We just have to add that 1 in there for our calculations. And now we have to change both the feet into miles and the seconds into hours. I'm going to do the feet first because they're the easiest part. The feet had to go on bottom so that they could cancel out. 1 mile is 5,280 feet. So the feet have now canceled. Now I need to get rid of seconds. Where are the seconds going to go so that they'll cancel? They have to go on top because they're on bottom here. So if they go on top, they'll cancel out. Now, to go directly to hours, I'd have to do some work. So I'm going to do this. I'm going to go seconds to minutes. 1 minute is 60 seconds. So my seconds are now gone, but I'm in minutes. So I want to get rid of the minutes and go to hours. So I'll put minutes here so they cancel. 1 hour is 60 minutes. So my minutes have now canceled. So now I have miles over hours, or miles per hour. So now it's a matter of multiplying straight across and then dividing this out. So I'm going to pause here. Does everybody see where each of these conversion factors came from? Mike, you look confused. Okay. I had feet and I wanted to get rid of feet. So I put feet on bottom so they would cancel out my fractions. Okay? And I'm changing feet into miles, so I put miles on top. So 1 mile, 5,280 feet. So now I want to get rid of seconds. Seconds are on bottom, so I have to put them on top so they'll cross cancel out. And I'm changing seconds to minutes because that's what the next step up. 1 minute, 60 seconds. Now my seconds have canceled out and I'm left with minutes. But I want it in hours, so I got to get rid of the minutes to go to hours. Okay? So I've got to put minutes here so they'll cancel out. Hours down here. 1 hour, 60 minutes. So now I've got to multiply across the top and bottom. So what each of this is, I did 3 conversions all at once instead of doing them one at a time. Is all I've done. So now across the top, I have 90 times 1 times 60 times 60 is 324,000 miles. Because miles is the only unit I have left on top. On bottom, it's 1 times 5280 times 1 times 1. So it's just 5,280. The only unit on bottom is hours. So now if I divide those, 324,000 divided by 5280, I get 61.36 miles per hour. Now how many of you think I can still throw that fast?
So,
No?
no. Maybe at some point.
We'll see again next year.
Maybe about.
If I warmed up, I could still throw but in the mid-60s. I could probably only get maybe 20 dozen to 20 pitches at that speed, but I can still throw mid-60s.
Can you guarantee the accuracy though?
Fairly well, yeah.
A strike every time?
Not necessarily every time, but the catcher wouldn't be diving for it. But like I said, I'd have to warm up first, and I'd probably only get maybe a dozen to 20 pitches, and then I'd be sore for 3 days. Yeah. That's why you guys are going to take my word on it, and we're not going to go prove it. So what we're looking at here is we're converting, guys, we're taking units that have more than one unit in it. This combination of units, the rates and stuff like that, and we're going to be converting those. For example, let's say that Drew's truck burns 1 teaspoon of fuel in, what do I want to do? What's that? Let's say it burns 1 teaspoon of fuel in 5 seconds at 60 miles per hour. Is that good fuel consumption? Is that a good fuel consumption? Who knows, right? No? Well, 20 miles to the gallon would be pretty good, right?
No. Yeah?
20 miles for your truck, yeah.
For a truck, yeah.
For a truck, yeah.
Oh, yeah.
You said fuel.
20 miles to the gallon if you're driving a truck would be good. So at 60 miles per hour, that would be about 3 gallons per hour, right? How do I get that? Yeah, let's go through this and let's take a look.
Wait a minute, where did the 3 gallons an hour come from?
That was off of the 60 miles per hour. And I'll show you what I did. I took 60 miles per hour. This can be thought of as 60 miles equals 1 hour, right? And what we said was a rate of 20 miles per gallon would be a good rate.
Yeah.
So how do we convert this miles per hour into gallons per hour? Well, this also could be thought of as being 20 miles equals 1 gallon. Any of these rates can be used as a conversion factor. So what I'm actually going to do is I'm going to take this 60 miles per hour, so 60 miles over 1 hour, and I'm going to convert the miles into gallons. right? No, I'm going to convert the hours into gallons, I should say. So I'm going to take, how do I want to do this? Ouch. I want it to be gallons per hour, sorry. So I'm going to put miles on bottom, gallons on top, 20 miles per 1 gallon. The miles cancel out. I've got 60 gallons in 20 hours. So that divides out to be 3 gallons per hour. So that's where the 3 gallons per hour comes from. Because I just used my rate as a conversion factor. Okay? So now we're going to use the 1 teaspoon every 5 seconds. Now we got to convert seconds into hours, so I'm going to do that. Seconds, hours. 1 hour is 3,600 seconds. I just did 60 times 60, so I didn't have to go through minutes. Saved me a step. So the seconds are now gone. The reason I did that is because to get from teaspoons up to gallons is kind of going to be a long conversion. We're going to go from teaspoons to tablespoons. 1 tablespoon is 3 teaspoons. So the teaspoons are gone, we're at tablespoons. From tablespoons to cups, 1 cup is 16 tablespoons. Cups to pints. 1 pint is 2 cups. So the cups are gone, we're at pints. 2 pints in a quart, you got it. And 4 quarts in 1 gallon. So, pints are gone, quarts are gone. On top, all we have is gallons, and on bottom we have hours. So gallons per hour is what we're going to get out of this. So we have 1 times 360 times 1 times 1, so it's just 3,600 gallons is on top. On bottom, 5 times 1 times 3 times 16 times 1, well, what is that? 15, 240, 480, 960, 3840 hours. Is that correct?
Wait, it's 1 gallon is 4 what?
5 times 3 times 16 times 2 times 2 times 4. 3840. So we're good there. So that's 3,600 gallons per hour. So 3,600, not gallons per hour, divided by the 3840 divides into 0.9375 gallons per hour. So now let's go to 60 miles per 1 hour. We'll put hours on top, gallons on bottom, because we're going to get rid of the hours, right? This is gallons equals 1 hour. In 1 hour, we burn 0.9375 gallons. That comes up to 64 miles per gallon. Now, a lot of people look at this and say a teaspoon of gas every 5 seconds. That sounds like a lot of gas. Most engines will burn about a teaspoon of gas every about 1.5 to 2 seconds, depending on the engine.
Yeah, that's
A lot of trucks will burn a teaspoon about every second.
yeah, that's 60 miles.
You're looking at what, about 13, 14 miles to the gallon? Yeah, that's a teaspoon every second.
13 gallons.
Yeah. So you're literally a teaspoon per second is what you're burning. Yeah, 18 would be about a teaspoon every second and a half. People think, breaking it down that way, we think a second is such a short period of time that it shouldn't take much in a second, but it does. Oh, let's see. What do we want to do here? For you guys, you're going to deal with like loads and stuff like that. If you ever go to the next step into design, you want to look at, let's say you've got something that is rated at, what do we want to do here? Four ounces per square inch. Well, how are we used to seeing loading for construction done? pounds per square foot. PSF, right? So how are we going to do this conversion? Well, this is 4 ounces over 1 square inch. We got to get rid of the square inches and the ounces. Since you said the inches, we'll get rid of those first. 1 square foot is how many square inches? Not 12. It's squared, so it's 144. So that'll get rid of the square inches. Now we got rid of the ounces, going to pounds. 1 pound is 16 ounces. So the ounces cancel out, the square inches cancel out. We have pounds on top, square feet on bottom. That's what we want. Pounds per square foot. So 4 times 144 is 576. Pounds over 1 times 1 times 16 is 16 square feet. Which gives us what? Is that 36? Pounds per square foot. 36 PSF. That's actually a relatively light load. Most floors are rated at about 60 PSF. Well, most roofs and floors are rated at about 60 PSF. Most of your roofs are 40-10-10 or a 47-10. And most of your floors are a 45-5-10.
I don't know what you would make a square foot and go pretty good.
Yeah. But a point that's a concentrated load, that's different. Live loads go. I don't want to get too far into truss design, but they're called duration factors. Like what percentage of the time would you be standing on that single spot? Basically what they're talking about.
So if you kept staying there, eventually it would break.
No. Because the floor system is designed to distribute that load out over more than just the direct spot you're standing on. So like rain has a duration factor of a 1.6, which means you divide its weight by 1.6. A human being is a live load. Usually you have an animal has a load of, unless it's livestock or something like that in a barn, but in a living space, human living space, a human usually has a duration factor of 3. So you would take your weight and divide it by 3 would be the actual load they would put on that truss at that point. But then there's factors for how it's distributed out over more than 1 square foot too. That's what I used to do. I used to do truss repair, stuff like that.
Hey, let's figure out how much pressure is on a woman's high heel. Say the high heel is quarter by quarter.
Quarter by a quarter, so it's a small one.
She weighs 110.
So that's a 16th of an inch, or 16th of a square inch, right?
She's standing kind of provocatively, so all her weight's on that one heel.
On one heel?
Yeah!
So that's 110 pounds on 1/16th of 1 square inch.
That seems too small for a high heel?
Nope.
Maybe we should say 3/8. Let's go with 3/8.
At a quarter by a quarter, that's you're looking at 1,760 pounds per square inch. Just dividing it out. 110 pounds divided by a quarter of a square inch. If it's 3/8 by 3/8, you're looking at 9/64. So that is 782 PSI about.
So the quarter has more than
Because it's smaller. But yeah, most high heels, the smaller high heels run around 500 pounds per square inch is what they're holding up.
I knew you would know that. I knew that.
They're dealing with a polymer in most cases. It's a polymer. It's a composite. It's a polymer fabric composite. So it's a carbon based. So yeah, and under compression, under tension, they would not hold up. But under compression, they hold their compression structure. They actually designed to actually have some give to them, is what allows them to hold up.
You have a way of taking sex right out of the whole equation.
I'm an engineer, you know. I'll pretend I didn't hear that. Let's say that you have a pump on a job site. Let's say you got a basement that floods, and you're gonna pump the basement out, and you got a pump that is rated at 40 cubic inches per second. Is that a good pump? Let's say you got another one. Your buddy has one that's rated at 12 cubic feet per minute. Which one's better? Well, let's take this one and convert it. 40 inches cubed in 1 second. And we got to convert it into cubic feet per minute. So we're going to put cubic inches down here, cubic feet up here. 1 cubic foot over 1,728 cubic inches. Where'd the 1728 come from? 12 by 12 by 12. 1 cubic foot is 1,728 cubic inches. Times, from seconds to minutes, of course, 1 minute is 60 seconds. So, of course, the cubic inches cancel, the seconds cancel. We do have cubic feet per minute, which is what we want. 40 times 60 is 2,400 cubic feet. Over 1 times 1728 times 1 is 1,728 minutes. So 2,400 divided by 1,728. You get 1.388, 1.39 cubic feet per minute. So 40 cubic inches a second sounds like a lot of water. It's not. Most of your pumps, your sumps that you use for a job site, are between 9 and 20 CFM, cubic feet per minute. So yeah, that's slow. Okay. Let's say you've got a piece of lumber. You got wood that has a density of, let's see here. Let's see, you look up wood, and the piece of wood that you're working with is 42 pounds per cubic foot. And you have what's that? That's the standard density for lumber. Well, hopefully there's not a cubic foot in a board. Actually, a lot of boards, there are boards that are up to a cubic foot. 2 by 6 by 12 is a cubic foot. And a 2 by 6 by 12, I'll tell you this one usually weighs more than 42 pounds per cubic foot if it's green treated. Let's say you have a project that you figure it out, and it's going to take you 4.5 board feet. Do you guys know the conversion between cubic feet and board feet? No? Well, you do know that 1 board foot is how many cubic inches? 144 cubic inches. So let's take it to cubic inches and we'll go from there, okay? So let's do 42 pounds per 1 cubic foot. I'll let you off the hook. One cubic foot is 12 board feet. What's that? Oh. So 1 cubic foot contains 12 board feet. A board foot is 12 by 12 by 1 inch thick. A cubic foot is 12 by 12 by 12 inches thick. So there's 12 of them in there. So we can cross cancel the cubic feet. This is 42 pounds per 12 board feet. If we divide that out, 42 divided by 12 is 3.5 pounds per board foot. And then times 3.5 or 4.5 is what? 15.75 pounds. Now here's another thing. If you're looking at this wondering, okay, I've got 4.5 board feet. Do I multiply or do I divide? You can use this as a conversion. You have 4.5 board feet. Put it over 1. I want to get rid of the board feet and just get pounds. Here I have 3.5 pounds is 1 board foot. So the board feet cancel out. I've got 4.5 times 3.5 is 15.75. It's just pounds because it's the only units left. Does that make sense? It's what we call dimensional analysis. You can use the units to tell you what your calculation has to be. Let's see here. Anytime you have a rate, let's say that you have a fluid that is 8.9 pounds per gallon. And you want to know how many pounds in 6 gallons. So what we're doing is we're starting with gallons and we want to change it to pounds. So we start with our 6 gallons, put it over 1. We're getting rid of gallons. This, remember, said is 8.9 pounds equals 1 gallon. So 1 gallon, 8.9 pounds. Gallons cancel out. It's 6 times 8.9, or what, 53.4 pounds. So if you get good at working with these units, this unit conversion tool is actually extremely powerful because it allows you to figure out how to do a lot of calculations even if you've never done it before. You can use the units. If the units cancel out and get you to the unit you want, you've done it correctly. What's that? That you didn't learn in high school? Let's say you do it incorrectly. Let's say you're driving at 60 miles per hour and you want to know how long it's going to take you to go 240 miles. Technically what we're doing here is we're converting from miles to time. So we'd want to start with the miles. Well, let's say you screw up and you do this. I got 60 miles per hour, 60 miles over 1 hour. And I put miles down here. I've got 240 miles, and there's nothing to compare it to, so I'm just going to put 1 above it. The miles cancel out. I've got 60 over 240 hours, which is 1 over 4 hours. I wanted hours, right? I wanted time, but it ended up on bottom. All I have to do is flip it over. Do the reciprocal. 1 over 4 hours is the same as 4 hours over 1. So it's 4 hours. That converts into 4 hours. What I did is I did this incorrectly.
Yeah.
But I got 1 over 4 hours, so the 4 hours is my answer. If I were doing this correctly, I should have done 240 miles, convert it into hours by putting miles down here and hours up here. 1 hour is 60 miles, because 60 miles per hour.
Yeah, you can just
See what?
one of the 4 hours is different.
Numerically it is, you're correct with that. But we were trying to convert miles into hours and we just did it wrong, so we ended up with 1 over 4 hours. What that's telling us is we did something wrong. Technically you're right, Mike. You should go back and recalculate it and do it correctly like I'm going to do here. So you start with the 240 miles, because what you want to end up with needs to be on top. You want to end up with hours, so there it is. It's on top now. So the miles cancel out. Now you have 240 hours over 60, and that does divide out to give you the 4 hours. But generally, if you end up with what the units you're looking for ends up on bottom, that means you did something wrong. You have to go back and flip your calculation over and do the whole thing over.
Okay.
But you can see this is that piece flipped over. This is that piece flipped over, so the whole thing ends up being flipped over. Okay, I am going to give you guys some problems to do out of the book, big book, and then I'm going to give you a packet to work on. In the big book, it's page 257, exercise 813A. Then on page 257, also exercise 8-13B. And then on page 258, exercise 8-14. And then I'm going to hand out a packet for you. In this packet, it'll be pages 91 through 93. Like I said, this is something I'm really going to kind of stress here because doing these compound unit conversions, if you get good at working with the units, the unit conversions from basically the last couple of weeks, combine that with working with the compound units, it actually can define how you do those calculations like we showed here with the miles per hour converting from miles into hours. Anything that's a rate can be used as a conversion factor. Okay, I will hand out the packets now too quick. Just so you know, do the recording still, so you don't have it. Oh yeah. I figured it's fair, don't worry.
Okay. I hope you get stressed enough. You can do 15 years from now and you have family and kids.
I even give you guys 7 minutes to start doing your homework.
I'm getting my head bobbed in your room.